then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students. Welcome to lesson 13. Okay, today's lesson is on the intermediate value theorem, also abbreviated as IVT. And it's a very interesting theorem. And today's lesson is going to be fairly short because we're really just going to focus on the theorem. We're going to look at, we'll explain the theorem, of course, and then we'll show why the conditions of the theorem must be in place. And then we'll look at a couple of examples, and that'll really be it. This theorem is pretty important. It's used to prove some things you do in some more complex problems a little more complex than what we're doing right now. But it's something that you always want to remember. So when we get deep into the course, there's going to be certain problems where you have to justify why you're able to prove something. And in a lot of cases, this theorem and some other theorems we'll do a little bit later, like the mean value theorem and the extreme value theorem, and also Rolle's theorem, which really you can just roll into the mean value theorem, are really things we use to justify particular things. And to be able to use that justification, we don't just need to know the theorem, but we need to know the conditions that must exist in order for us to utilize the theorem. So with that said, let's take a look at the theorem. All right, so intermediate value theorem, IVT. And by the way, if you ever had to justify something on the free response problem, either doing a problem for me or on the AP exam, and you were justifying it through the intermediate value theorem, writing IVT is a recognized way of showing that's the intermediate value theorem. So you can abbreviate it by IVT. It's well recognized. All right, but anyway, so the intermediate value theorem, IVT, states if f is continuous, and notice I underline continuous, that's pretty important. It's continuous on the closed interval AB, and f of A is not equal to f of B, and K is a number between f of A and f of B, then there is at least one number C in AB such that f of C equals K. I know for some people, when I read this and when they're looking at this, none of this seems to make sense. And so my job is to make this make sense. But like I say, this is a very technical course, and every word and statement in this statement is particularly important. So I just want to highlight what it's saying again, and then I'm going to illustrate it from a graphical standpoint. So we talk about understanding the conditions that need to be set fit for this particular theorem. The main thing is that the function must be continuous. And it says continuous on the closed interval AB. A closed interval means you include the endpoints. So those of you familiar with interval notation, and you know we put brackets on the number when the numbers are included and parentheses when the numbers are not included. So a closed interval is an interval where the endpoints are included. An open interval is an interval where the endpoints are not included. So this should be continuous on the closed interval AB, and also f of A and f of B should not be equal. That means the y values. So, you know, A and B are x values, f of A and f of B are the corresponding y values. And it just says they shouldn't be equal. And again, when I show it from a graphical standpoint, you understand why. And K is some number between f of A and f of B. And then it says, then there should be at least some number C that's in A and B. So C is between A and B such that f of C equals K. Now this is what is called an existence theorem, meaning it just states that such a number C where f of C equals K exists. It doesn't tell you how to find C or how to find K. It just says such a number should exist. So let's expand a little bit more on this theorem with a graphical illustration, and maybe it will make a little bit more sense. Okay, so consider this paper the Cartesian plane, and I'm not going to label an X and Y axis. Those lines would get in the way of what I'm trying to do, but this This is a coordinate plane. And I'm going to label two values. So this is where x is A, and this is where x is B, and this point is f of A. The y value is f of A, and the y value here is f of B. So there's some number k. Now again, f of A and f of B, they're measured on the y-axis. Those are y values, so they're measured vertically. So there's some number k between these two. Some number k anywhere between these two. It doesn't say k has to be in the middle, just anywhere between these two. So say there's some number k, and I'm going to draw a line where f of x is equal to k. So say there's some number k in between these two numbers. What the theorem is saying is there is at least one number c that is between A and B. So there's some value between A and B such that f of c equals k. And what that's stating is, if I have a continuous function, so I'm going to graph a continuous function. It can be as crazy and as outlandish as you want it to be. So here's some function. But again, I have to make it to f of b. So if you look at it, eventually I have to cross k to make it to f of b. And that's really all the theorem is stating. If k is a number between f of a and f of b, at some point between a and b, you're going to have to cross k to get to f of b. And that value, that x value, I made it awfully close to b. Probably should have made it a little further apart, so I'm going to slant my line to make some distinction. So that x value, where it hits k, is c. So from right here, we can see f of c equals k. And that's all the theorem is stating, that to go from f of a to f of b, if k is a number between those two values, you're going to have to cross k at some point. So it's going to have to be, and it has to be some value between a and b. I'm going to have to cross k at some value between a and b. It doesn't matter how you try to do it. You're going to have to cross k at an x value that is between a and b. Now, why does the theorem say that the function f must be continuous? Would this not happen if the function was not continuous? Well, let's take a look. So again, this is where x is a here. This is where x is b. I try to make it as similar as I can to the previous drawing. This is f of a on y. This is f of b. And then we have this value k somewhere between, anywhere between a and b. Doesn't really matter, as long as it's between a and b. Between a and b like this. Again, I mean between f of a and f of b. F of a and f of b are y values. Now let's say f was not continuous. So here's some function that's not continuous. So let's say you stop here, close circle, open circle, and we bam. So that's why the function has to be continuous, because if the function is not continuous, then it is possible that the function can make it all the way to f of b without crossing k. So this is the reason that the stipulation is that the function must be continuous. So that's why that stipulation is set, and that stipulation is very important. When you learn all of your theorems, you know, your main theorems, your IVT here, your extreme value theorem, the mean value theorem, they're going to be conditions. The main conditions are going to be whether the functions are continuous or whether the functions are continuous and differentiable on a particular interval. This guy only needs to be continuous because nothing in this theorem deals with a derivative. The theorems that deal with derivatives, they're going to say that the function needs to be continuous and differentiable. So really, those are the main two conditions when we look at these theorems. And when I say, I mean, we do a lot of theorems in this course, but there's the IVT, EVT, and NVT are kind of in their own little lane. In those particular theorems, we need to pay close attention to whether they're continuous or differentiable. And a little bit later, you understand there's a relationship between being continuous and differentiable that goes a certain way that we'll get to a little bit later. So with that said, let's look at a couple of little basic examples, problems involving the intermediate value theorem. All right, so here is a problem. And I know if you look there, you see 12 problems. I'm only going to look at 2 of these problems because there's some good problems that I want to save for your assignment. So don't expect all of the problems on your assignment to be like this particular problem, because I like you to think. So the problems you see on your assignment are going to be a little different. It's going to cause you to think. But if you think about what the intermediate value theorem represents, when you come across those problems, you should be able to figure them out, but we'll see how you do. Okay, so let's read this problem. So it gives me this function f of x, which is x squared plus 3x minus 10, and it says it's continuous. Now, one thing I have to mention, particularly when you start doing free response problems and you want to utilize these theorems, generally they have to tell you that a function is continuous or differentiable. Now, of course, f of x squared plus 3x minus 10 is a polynomial function. And so that's definitely going to be continuous. But, when we get into the swing of things, the functions are going to be a little more complicated. And it's going to be very hard for you to figure out if it's continuous or not. And some of the functions are going to be represented by a finite number of points on the table. And so they're going to have to tell you that the function is continuous. So in those situations, never assume that a function is continuous. They need to tell you if a function is continuous or not. But anyway, so it tells me here the function is continuous on the interval -2 to 2. So you see there's a closed interval there from -2 to 2. And it says if c is any number between -2 and 2, then which is possible for f of c? So c is a number between a and b. In this case, a is -2 and b is 2. And I said, what is a possible value for f of c? Well, it has to be a value between f of -2 and f of 2. It has to be a value. So this is like the k. It has to be a value between f of a and f of b. So in order to determine which of these could be the answer, and again, the theorem doesn't tell me exactly what the number is. It just tells me that the number has to be between my f of a and f of b. So to figure out which of these numbers is between f of a and f of b, for this problem, we need to find f of a and f of b. So I need to find f of -2 and f of 2, and I'm just going to pick the value that's between those two values. So pretty basic. Let's take a look. Well, let me write down this function first. So the function is x squared plus 3x minus 10. And my a is -2, my b is 2. And just understand that f of a doesn't necessarily have to be less than f of b. The only distinction is that they must be different. And I really didn't address that in the problem, but I think it's pretty easy to understand why in this theorem it says f of a and f of b cannot be equal, because just quickly, again, f of a and f of b are y values. So if they're exactly the same, how can I put a value k between them? They're equal. There's no way I can get a value between them. They're equal. So in order to put a number between them, these guys cannot be equal. So that's why they can't be equal. But it doesn't mean that f of a has to be less than f of b. F of a could be greater than f of b. They just can't be equal. All right, so let's get back to this guy. So let's find f of -2. So f of -2, that's -2 squared, that's +4. That's 3 times -2, that's -6. 4 -6 is -2, and -2 minus 10 is -12. And let's find f of +2. So that's 2 squared, that's +4, and then that's 3 times 2, that's 6. 6 and 4 is 10, and then -10 is 0. So By IVT, if C is some number between -2 and 2, then there has to be, then f of C must be a value that's between -12 and 0. So I just look at my answer choices, and there only should be one answer choice that is between -12 and 0. So let's take a look at the answer choices. And here it is right here. This is the only number here that is between -12 and 0. That's the only number. So on these type of problems, of course, only one number can be within that range, or else you would be able to select multiple answer choices. Now, in a theorem, it doesn't necessarily mean that there's only one value for the whole function that equals that number. The theorem says there's at least one, but of course, to write a multiple choice problem, we're not going to have more than one answer choice where the value is true. But theoretically, if you just take a look from a graphical standpoint, so if you just think about it, so let's just say this is f of A and this is f of B and this is K right here. The function could be equal to K, at multiple values. So the theorem says there is at least one, but there of course could be more than one. Okay, let's look at another example. All right, so here's the next problem. So you should be familiar with this type of problem since we just did one. So this is the point of the show where I ask you to pause the video and work the problem yourself. Okay, so you should have worked the problem. Okay, so here's the function. So my A is -4, my B is 2. So let's find f of -4, and that's going to be -2 times -4 squared. That's 16 times -2. That's -32 minus -4. So that's going to be +4. So I have -32 plus 4. That's -28. Plus 4 plus another 4, that's this 4 right here, that's -24. And then f of 2 is -2 times 2 squared, that's 4 times -2, that's -8. So -8 minus 2, that's -10, plus 4, that's -6. So I'm looking for an answer which is between -24 and -6. I'm looking for an answer choice which is between -24 and -6. Now let's take a look. So let's see what's between -24 and -6. That would be this guy. All right, so that's going to conclude our short lesson on IVT. Again, I'm going to have some interesting questions on IVT on your assignment. Hopefully you're able to tackle them. We'll see you next time.